everyone, and welcome to today's session on the implications of room temperature and ambient pressure superconductivity. I'm your host, David Dreyer. I'm a solution principal at SAP America, specializing in digital manufacturing and Industry 4.0 in supply chains and manufacturing operations. I'm excited to be joined by an esteemed panel of subject matter experts to discuss this fascinating area of research and experimentation and what it could mean for manufacturing, supply chains, and society as a whole if realized. This is one of a series of regular podcasts that I'll be hosting. The format I'll use will be roughly 15 to 20-minute podcast sessions, supplemented with a transcript of the session and a complimentary blog post that will cover the related content more objectively. In today's episode, we'll be exploring the potential impact of room temperature superconductors. With me are three leading experts who will share their perspectives on the opportunities and challenges of this transformational technology. It should be an engaging topic. However, as a preface to this podcast, and in the interest of full disclosure, I want to make clear that the personas you're about to hear, including my own, are all synthetic creations of generative artificial intelligence. The insights shared here are an amalgam of knowledge from the large language model developed by the private company Anthropic. The personalities and backgrounds represented here are purely fictional, although the insights and domain knowledge are genuine and derived from the generative models available today. And so this podcast series is a creative experiment to share important knowledge on the frontiers of science and applied technologies through the voices of synthetic experts who express insights based on actual domain expertise. To begin, I'd like to provide just a bit of context around superconductors. For our listeners who may be unfamiliar, superconductors are materials that can conduct electricity with near zero resistance when cooled below a certain temperature. This allows for incredibly efficient electrical systems and power transmission, but to date, superconductors only work at extremely low temperatures, requiring very expensive cooling. Room temperature superconductors would remove this cooling constraint, revolutionizing electrical systems and enabling new capabilities across industries. So, without further ado, let's begin. As our expert guest, we have first Dr. Mary Caldwell, a leading materials scientist and pioneer in high-temperature superconductors. Next is Dr. Kevin Wu, a veteran electrical engineer focused on translating new discoveries into real-world applications. And finally, we have Dr. Lee Robertson, an ethicist who studies technology's impact on humanity. Thank you all for joining us. I'd like each of you to briefly introduce yourselves, including your background and interest in this field. Let's start with you, Mary.
Thanks, David. I'm delighted to join this discussion. As you mentioned, I'm a professor of materials science at Stanford University, focused on discovering new superconducting compounds. I got interested in superconductors as an undergrad because the idea of perfectly efficient power transmission seemed almost like science fiction, and I've been hooked ever since. My team uses computational methods to predict stable and high-temperature superconductor candidates. It's challenging work, but the potential payoff for society makes it incredibly rewarding. I'm optimistic we'll get there in the next decade or two.
Thank you, Mary. Nice to have you with us. And Kevin, welcome.
Thanks, David. It's great to be here. I'm Kevin Wu, lead systems engineer at Teradyne, where I focus on superconducting device integration. I hold electrical engineering degrees from Cornell and MIT, and I've worked in R&D engineering for over 15 years. Incidentally, researchers at Cornell are today involved in experimenting with new materials for room temp superconductors. My passion is developing practical applications of new materials discoveries, like higher temperature superconductors. I collaborate closely with basic researchers like Mary to take their superconductor candidates from the lab into prototypes. There are always hurdles translating theoretical potential into commercial reality. We've been discussing and investigating room temperature superconductors for 70-some years now, so continued progress will require patience and persistence. But the capabilities truly ambient superconductors could enable make it well worth the effort. I'm looking forward to a thoughtful discussion on our topic today.
Thanks, Kevin. And finally, Lee, please introduce yourself.
Greetings, everyone. I'm Lee Robertson, professor of science, technology, and ethics at Georgetown University. In addition to my philosophy background, I have cross-disciplinary degrees in electrical engineering. I've written widely on emerging tech ethics and governance. I study how emerging technologies like superconductivity interact with society and human values. It's crucial we consider ethical dimensions in addition to technical benefits early on. I'm genuinely encouraged by the potential societal benefits, but also believe we must pursue progress wisely and humanely. True success requires foresight, collective responsibility, and moral courage. I'm excited to explore these topics today.
Thank you all for your introduction. What a diverse range of expertise we have here. Now let's dive into the implications of this technology and considerations around responsible innovation. Mary, let's start with you. What capabilities do you envision room temperature superconductors enabling if and when realized?
Sure. There are so many potential applications. Fully efficient electrical transmission without losses would enable advances like room temperature MRI machines without liquid helium cooling. Also, levitating high-speed maglev trains and compact particle accelerators, transformers and motors with unprecedented power densities. We could see a new era of electric aviation and shipping, and of course, lossless computing in data centers. It may sound like a reach, but superconductors operating freely at room temperature could fundamentally transform how we power the world.
Thank you, Mary. I'm somewhat familiar with properties of noble gases like helium, specifically its inert, non-reactive atomic state that makes it non-combustible, but I wasn't aware of its use in liquid state for MRI machines. Can you elaborate on that a bit more and explain how room temperature superconductors would play an important role in that application?
Sure. Well, an MRI machine contains coils, a magnet and wires that conduct current. The machine uses a great deal of energy because of its large magnetic field. In order for it to use that much energy, it must be superconductive. For this to occur, wires inside the machine need to be reduced to a temperature of near absolute 0 degrees. The machine requires a substance for it to maintain such an extreme cold temperature, and that substance is liquid helium to supercool the internal wires continuously. The fluid has a temperature of -269 degrees Celsius, which is the equivalent of -452 Fahrenheit. The average scanner machine utilizes around 1,700 liters of helium. The amount of helium in an MRI scanner must also be topped off on a regular basis, thus increasing the amount of helium used by the machine even further. Unfortunately, the amount of helium on Earth is diminishing due to its heavy usage, and it's escaping from our atmosphere. There isn't much of it on Earth because it's not weighed down to the atmosphere. It's slowly but continuously floating off into space. The noble gas is unable to be synthesized and is usually made through natural radioactive decay. But in geologic terms, it takes hundreds of millions of years to produce any substantial amounts that can be extracted from the Earth. Once the helium is gone, it's gone forever as a non-renewable resource. The medical field requires a large quantity of helium to assist patients with diagnosing and monitoring their condition, which is certainly a vital and valued use. But that's where a room temperature superconductor would become so valuable, alleviating our dependency on a non-renewable natural resource.
That's fascinating, Mary. Thank you. Kevin, your thoughts?
I agree the capabilities could be transformative, but we must be realistic about the timeline and hurdles. We've been striving for practical room temperature superconductors for over 50 years without success. Realizing even a fraction of their theoretical potential could take decades more. We still lack basic theoretical understanding of how electron pairs manage to flow unimpeded at higher temperatures. And we face engineering challenges like material stability, manufacturability, system integration, and cost. We must celebrate incremental progress while maintaining patience and perspective.
And Lee, what observations from you?
You both make excellent points. I believe the ethical pursuit of progress requires concurrently advancing theoretical knowledge and practical applications. We must avoid both unfounded hype and short-sighted skepticism. Collaboration is key. Isolated brilliance alone cannot overcome complex challenges. To achieve collective breakthroughs, we need policies that cultivate a stewardship innovation mindset focused on opportunities and responsibilities.
Yes, I agree with you, Lee. We should absolutely pursue this technology with wisdom and care for societal impacts, but we must also keep thinking ambitiously, with enough imagination, rigor, and transparency. I'm confident we can build an electric world that exceeds our boldest visions while also lifting up humanity, but we will need macro policies to accelerate research and development.
Steady investment in both basic and applied research is critical. But policies also need to ensure open collaboration and knowledge sharing. Proprietary solutions and isolated competition could seriously delay or derail progress in this space. We need secure international databases for sharing superconductor candidates and research findings.
Those are all great perspectives, and you raise important considerations around responsible conduct and policy frameworks that could accelerate progress. Lee, from an ethics perspective, what responsibilities should researchers and innovators prioritize to ensure room temp superconductivity benefits society?
We must carefully evaluate both opportunities and obligations from the outset and consistently revisit them. Researchers have a duty to make social impacts a priority, not an afterthought. We need proactive ethics training and oversight integrated at every step, from lab research to commercialization. Policy should require ethics assessments for funding, and we must uplift the voices of marginalized communities to avoid bias and hubris.
I agree, Lee. Researchers want to help humanity but can lose perspective in the competitive drive to innovate. Policymakers should establish innovation standards that embed ethics, safety, and reliability by design. This includes fail-safes, monitoring for dual-use potential, and protective coatings for ambient superconductors. Standards help innovators align with ethical priorities.
Those are smart recommendations. We can also foster responsible, secure collaboration through international innovation ecosystems, formalizing partnerships between academia, government, and industry. Joint oversight and IP sharing with reasonable licensing fees and public sector use rights. We need ambition guided by wisdom and integrity.
Very important points on our need for stewarding progress responsibly. Let's shift to policy opportunities. What role should governments play to accelerate development while managing risks?
Governments must fund comprehensive innovation pipelines, both exploratory research to discover new materials and engineering to translate discoveries into products. Balancing long-term knowledge gains with commercial viability, rapid prototyping and scaled pilot projects can de-risk new technologies for private sector adoption.
Yes, great points, Kevin. Governments also need to grow a diverse, interdisciplinary STEM workforce equipped to excel in this space, and establish incentives for private sector R&D while discouraging proprietary lock-in. We need collaboration, not siloed competition. With inclusive vision and smart policy, we can build an innovative ecosystem poised for breakthroughs.
Mary makes a key point. Progress will depend on expanding human empathy alongside technical prowess. Let us walk this path with care, curiosity, and moral courage. Technological revolutions require social revolutions too.
Thoughtful perspectives all around. And what about safety consideration?
Well, since we're dealing with extremely high electrical currents, safety is paramount. Superconductors can conduct hundreds of times more current than copper wires of the same size. Without fail-safes, a malfunction could generate intense magnetic fields or arcing. We need integrated monitoring systems to cut off current during anomalies before damage ensues. Active cooling engagements can also trigger during faults to intentionally stop superconduction.
Those are great points, Kevin. Another approach is passive or intrinsic fail-safes built into the material itself. Adding small amounts of silver or gold nanoparticles, for example, can induce resistivity during excessive currents while maintaining superconduction under normal operating conditions. The goal is to avoid catastrophic failures even in unpredictable environments.
That's true, Mary. Protective coatings will also be critical, both for stability and containing magnetic fields. Refractory metal oxides or nitrides applied in nano-layered structures can shield room temperature superconductors from oxygen and moisture. And metallic outer layers like tin or zinc can attenuate magnetic fluxes emanating from the supercurrents. Multi-layered coatings are ideal to combine these functionalities.
It's encouraging to see thoughtful solutions emerging to manage risks proactively. Beyond technical protections, we need open disclosure of safety incidents to promote collective learning. And design standards should incorporate defense in-depth principles with redundant fail-safes and layers of protection. This reflects the integrity and care required to earn public trust.
You're right, Lee. We have to design safety both into the technology itself and the culture around it. With transparency, vigilance, and wisdom, we can build an electric future that's not only efficient but resilient.
Excellent perspectives all around. It's clear that realizing room temp superconductors safely will require just as much care and creativity as the basic science itself. What other domains do you see as ripe for disruption?
The healthcare potential is astounding, from MRI machines, as mentioned earlier, that don't require expensive cooling, to particle accelerators and non-invasive proton therapy for cancer treatment. But we must ensure equitable global access to these benefits, not just the wealthy few.
In theory, superconductor levitation could enable frictionless, high-speed rail travel, but retrofitting national rail systems would require massive investments.
The travel efficiency would be worth it. But you're right, the infrastructure overhaul costs present a major barrier. Gradual integration is probably the more prudent approach.
Governments must weigh those infrastructure expenses against social benefits. Travel made affordable for all citizens should be the goal, not accruing private profits.
From an engineering perspective, transitioning rail and shipping infrastructure globally to use superconducting systems would require just an astronomical investment. We're talking trillions of dollars to upgrade networks, retool assembly lines, and design new standards. And frankly, I'm not yet convinced the returns would justify replacing current high-speed rail and electric vehicle technologies that are working well enough.
I agree. Major investments will be required, but assets could be stranded if better materials are discovered. Policy incentives should favor modular designs to maximize reuse potential.
I really believe the increased efficiency and sustainability could motivate those expenditures in time. Especially as climate change concerns mount, improving transportation energy usage and emissions has to be a priority. But you make fair points on weighing costs. That's why I think public-private partnerships can distribute the infrastructure investments fairly, while policies incentivize the long-term environmental payoffs.
Supply chain optimization is promising, but we must safeguard against misuse. Rogue actors could exploit ambient superconductors to disrupt power grids or data centers. We need cyber-secure design standards.
Yes, agreed on that security concern. And while manufacturing productivity gains appeal to business interests, we can't neglect safety. Policymakers must mandate redundancies, fail-safes, and worker training for high-current applications.
All true. We should maintain cautious optimism. Overhyping potential timelines risks disillusionment, but dismissing challenges breeds complacency. A balanced perspective is key.
Right? Our history with new innovations entering a long hype cycle only to plunge into the trough of disillusionment is a cautionary tale.
Okay, so we've touched on some of the applications like MRI machines and transportation, but I want to dig deeper into what new technologies and capabilities room temperature superconductors could enable. Mary, what other promising applications come to mind from a materials science perspective?
Well, one other area is quantum computing. Superconductors can enable quantum bits or qubits with long coherence times, which is critical for performing calculations and error correction. Room temperature versions could greatly simplify the cooling systems required for quantum computers today.
Fully agreed. The potential to revolutionize quantum computing is huge. Beyond that, I'm excited about applications in data centers and computing. Superconducting power cables alone could save massive amounts of electricity.
Those are great examples. I also envision breakthroughs for sensors and medical devices, since superconductors can detect very minute magnetic fields and electrical signals. High-resolution brain imaging and neural interfaces come to mind.
Excellent points so far. What about outside of computing and electronics? How might superconductors change other industries?
Transportation could be disrupted in a big way. Levitation trains are just the start. Shipping and logistics may no longer rely predominantly on diesel trucks and legacy infrastructure, and we're already seeing autonomous electric vehicles find commercialization in long-haul fleet carriers. I also think construction and infrastructure would change drastically as well. Things like lossless power transmission lines become feasible on a large scale.
I'm also very interested in the business model implications. Supply chains and manufacturing would be far more dynamic and optimized if energy costs and losses disappear as constraints. Entirely new business models could emerge with more diverse software as services and microservices potential.
Faster computing could enhance access to knowledge but also potentially widen the digital divide. Progress must uplift marginalized communities, not leave them behind. We need policies to increase broadband access.
I agree the potential is amazing, but also share concerns we must mitigate proactively. Concentrating so much processing power raises serious ethical questions about oversight, transparency, and bias mitigation. Without careful governance, supercomputers could easily be misused to suppress dissent and consolidate wealth and power. We need policies as enlightened as the technology itself.
That's another important point. We really need to monitor for unintended consequences and inequities. Ongoing ethics assessments and public dialogues can identify issues early before harm grows severe.
You both highlight valid concerns. Realizing such profound potential requires a commensurate sense of responsibility from the start, not as an afterthought. We must embrace opportunities while exercising wisdom, foresight, and care.
Superb perspectives. Thank you all. This discussion has underscored the nuances we must thoughtfully navigate, but also why navigating them is so important for society. Thanks, everyone, for such an engaging, thoughtful discussion on the opportunities and obligations around developing room temperature superconductors. As we wrap up, I'd like to go around for any final reflections. Mary, could we start with you?
Well, realizing this technology in a responsible way won't be easy, but the potential is too meaningful not to pursue. If we maintain society's trust through ethics, safety, and collective benefit, I believe room temperature superconductivity can help build a more just and sustainable world.
Well said. This journey requires patience, but not complacency. With diligence and wisdom, we can progressively turn theories into realities that improve lives. But we must always prioritize people's well-being over profits or prestige.
I appreciate those perspectives. I agree we have a duty to explore this promise, but with more than technical prowess alone. We need humility, courage, and moral imagination to elevate human dignity through scientific advancement.
Great final insights from you all. And thank you, Mary, Kevin, and Lee, for taking part in this inspiring discussion. You've given our listeners much to contemplate. I hope these insights on opportunities, obligations, and shared progress stay with our audience as room temperature superconductivity continues being explored. And so, that concludes this episode of Modern Matters. Until next time, stay curious, stay tuned, and keep learning about the technologies poised to change our world. Bye for now.